consider different classifications. Okay, it is not that all of them are excluded. That they will anywhere you will find they intersect. Okay, these are like what I felt, because if you see in papers or especially in the books, everywhere you will find that is they classify the uncertainty according to only this, depending upon their structure. They are structure, parametric, or maybe lumped. But from my experience, what I have seen, that is not only this one. Maybe this is the most common type of classification, but there are many other categories. So that's why today I thought of introducing the other categories which I have come across here and there. As I said, that is today, first half an hour we will discuss the uncertainty classifications, although that is most of the things we have already learned, but there are some more. And also that is what is the main purpose. As I said, that is if you see the books, mostly the first class or mostly the first category is discussed, right? That is if you see what is the classification of uncertainty, most of the places you will find they write structure, parametric, and maybe lumped as well. But there are many other categories. So that's what that is I said. When that is you study more and more, not only the books, even the papers also, then there is you might have a confusion. That is okay. There are some other kind of, not maybe I'm not saying that these are completely separated from this. They will also, that is some of them, or rather all of them, you will find it is coming as a mix and match with this, right? Because why? Because in the unstructured uncertainties, that is something that is about which we don't have precise information, and we model them. If it is in the frequency domain, why we prefer frequency domain? Because it can be modeled as a transfer function. And then, that is, if it is a stable transfer function, it will belong to the space of Ra infinity. Finding the norm is really easy, and we know we have the M-delta structure. Then it will help us in analysis, also for controller synthesis. That's why most of the time we wish to represent the uncertainty in the frequency domain, right? But now, that is, if it is originally, if you see the uncertainty, it can be a static, it can be a dynamic, right? It can be time varying, it can be time invariant. Similarly, that is, it can be real, it can be complex, lot many things, right? So if it is a real, and then if it is time invariant, that is nothing but parametric uncertainty. Again, a parametric uncertainty can appear in a transfer function as well as in state space. So what I wanted to say, that please don't think that is each category, they are completely separated from other. So there are, that is, we are classifying the uncertainties with respect to different properties. Okay, like first one is with respect to their structure. if the structure is known or not known, or whether they are coming as a lump. The second one, whether it is a static uncertainty or dynamic. Static means it will be regulated by an algebraic relation, dynamic means it will be related by a differential equation, right? Then time invariant, time invariant. That means suppose it is a static uncertainty, but it can depend upon the time, it may not explicitly depend upon time, okay? In that way it is time varying, time invariant. Then real or complex. Of course the uncertainty, it can be real. Say for example, if you have a spring mass damper system, then each of this mass, then spring constant and viscous friction coefficient, they can vary within a range, okay? So that is a real uncertainty, parametric uncertainty. So that will be real. The complex means now for the dynamic uncertainty, even for the static uncertainty also, that you can see that it is not only real, it can take the complex conjugate values. That can also be a type of uncertainty, right? Say for example the unstructured uncertainty or the frequency domain. Ultimately you will find their variation is not only in a plane, like not on the real axis. It has an imaginary component as well if it is translated into the Cartesian coordinate. So that in that sense it will be a complex, right? Then it can be like already we have discussed about that is norm-bounded, bounded real, phase restricted. This is somewhat 50% to 60% you already know, remaining we will discuss. This is completely new, we will discuss, this is also. So except for the last three, the remaining ones I hope you have understood, right? And what is the main purpose? So that like after this analysis, because I know like especially for the PhD students, they have a lot of like doubts or confusion regarding the uncertainty. So that's why I thought that it's not only them, for you also. Like this one we all know about it, even though the books are in all the books, it's quite common. But here and there you will find this kind of terms. Then you may fall into a confusion that is, we knew only this, but now I am seeing whether it is real or complex, time invariant, time varying. So ultimately in which of these categories or in which of this class they will fall. So to clear those confusions, that is I am writing all of them, okay? Just now that is whatever you have learned so far, you just try to identify or you just try to like check whether you are confident with these new classifications or not. Are you confident with this new classification? That you just check, okay? When we talk about non-bounded uncertainty, that means we write it in the form like delta x comma t. You can write, sir, why you are writing x comma t? Because when you have non-bounded, that means that if, of course, it will depend upon the system, and in delta of x comma t means it depends upon x. Not only that, it can vary with respect to time. Okay, so in that way, the uncertainty that is represented in this. Not only this much, I'll have to add one extra condition. Why? Because the name suggests norm-bounded. So here, that along with, you have to always write its norm less than down. Okay, now this norm in which sense? That I don't know. That is, if it is a like now it is a time domain, then that is you can write 2 norm, you can write infinity norm. That depends upon that is which metric you are choosing. Okay, because of course it can be, it is either in the very simple case it can be a scalar. If it is one in system and also if it is one dimensional uncertainty, only in that case it will be a scalar. Otherwise it will be a matrix. Now if it is a matrix, if it has time varying terms, then that is which type of norm you will choose, that will come later. But that is when it is saying norm bounded, then always the norm condition must be there, right? Now that is within that is here, as I have written T explicitly, that means it can be time varying, but under some special cases it can be time invariant. If it is time invariant, depends upon the system but doesn't explicitly depend upon time, then and along with if now I define H infinity now less than gamma, then it will be a type of bounded real uncertainty. And most commonly, whenever we try to we discuss bounded real, we try to represent it in the frequency domain. Right? Rather, instead of this one, we prefer delta of S. But please don't think that is in time domain we can't represent. So that is one of my objectives. That is, I always emphasize that is, please don't bear a thinking that is okay. This can be, or some of them is specifically developed for time domain, some of them specifically developed for frequency domain. It is not. Uncertainty is a thing which depends upon the system. Now it is us, that means it is the control engineers who decides or who designs the uncertainty, or rather not design, modeling. That's why there is uncertainty modeling is important. Depending upon the available information, the physical characteristic of a system, that is we decide or rather we try to model the uncertainty. Now that is if the variation is within a bounded range, then we prefer frequency domain modeling. Why? Because we know that is if we represent in the frequency domain through a transfer function, then readily that is this H infinity norm, all those things would be available. And then there is a type of unstructured uncertainty, additive, multiplicative, inverse, whatever. All those techniques which we have learned, they will then be applicable, right? And this N delta structure, everything, those are quite systematic way and we have already learned. Because of the availability of those tools, we most of the times we try to represent them in the frequency domain. Because suppose if it is in time domain, then always you will have to go by the state-based approach. And then in the state-based approach, if you have multiple sources of uncertainty, then that is you have to first model that B1 and C1 matrix. Are you getting what I am saying? Whenever we talk about the generalized plant, in the in the time domain of the state space, how does it look like? X dot equals to Ax plus B1W, B2U. Then Z equals to C1X, D11W, D12U. And Y, or the measure output, C2X plus D21W plus D22U. Now this B2 and C2, they are the original B and C matrices of the plant, right? But that B1W and then there is the other one, that is C1X. Those things you will have to design, or rather they are the part that is which comes with the uncertainty W, or rather not C2, C1, that is the matrices which come with W that you have to model because they are related to the uncertainty. Now that thing could be little bit trickier. You must have some data from the experimental validation that what will be the coefficients of the D matrix. Are you getting what I am saying? X dot equals to Ax plus B1W plus B2U. Then Z equals to C1X plus D1W plus D22U. And Y equals to C2X plus, sorry, my notational mistake, D11, D12, this is D11, D2. Now what I said, that is this B2, this is the original B matrix of the nominal plant, right? That is, if you write G0, that is ABCD, then your B2 means the original B matrix. This C2 means your original, this is original B matrix, this is original C matrix. And your D22, that means your original D matrix, right? Now, that is what are the remaining? That is this C1, you can easily find it out. D1 to that too you can find it out. Like last day, if you see the example which we solved, like when you have a the block diagram of one plant and the controller, and you have like source of uncertainties and then disturbances, everything. That is when you write their equations, then immediately the construction of C1, then D1 to they will be clear, right? But D1 and D11, D21, they will also eventually become clear to you, but you have to decide that is how they are appearing. Now you can argue that is the case study which we had, we didn't have to model. Everything came up automatically. Then that is you were saying that we have to design or we have to model, but the case study that we considered earlier, there was nothing for design. What I wanted to say, the difference is, if you remember, there I directly wrote that this is a disturbance, right? And then when you have there directly that is coming as a signal. Now it may happen that is D0, that is if you directly the D0 is being applied, then in the modeling or in the controller design it would be difficult because you don't know that is how much is the range of D0 because it is not a reference input, it's a disturbance. So if you have to model a disturbance or an uncertainty, then rather than directly writing it as a signal, that is we try to model it D0 equals to BD into D0 bar. Like here, that is how are you getting? That is you have a signal which is an uncertain signal or a disturbance signal, then you are representing it as a matrix into a signal where this is quite defined to us. Maybe this will be norm-bounded or maybe this is a L2 bounded signal. Where D0 bar belong to L2 or rather we can write LT. This is called the uncertainty modeling or rather one part, rather you can write disturbance modeling, okay? So what did I say? That is, suppose there is a disturbance signal or there is a signal coming from an uncertainty block. Maybe one signal is coming from the noise. If you directly wish to work with those signals, it may be difficult for us to handle because whenever it's a disturbance or a noise or maybe a unwanted signal which is coming from the uncertainties, then we don't know they are bound or they are spread, they are spectrum. Those things are not known to us. Now that signal, if it is modeled like this much, like a matrix, into another signal which is bounded, then that is what is the advantage? First of all, that finally that in our like design, D0 won't appear, D0 bar will appear, which is bounded, whose pattern we know to some extent, and this matrix, it can be a column matrix, it can be a different type of matrix, like BD, this will directly be a part of the state-based representation. Then it will help us in the controller design. If it appears only as a unique signal, only D0, then we cannot accommodate it within the state-based. It will appear, suppose instead of BW, I cannot write a matrix over here, I am simply writing that D0. Okay, fine. When we do that, then also that is we have a knowledge or we have a hope in mind that is okay, they are slowly varying disturbances, like a step disturbance or even ramp, kind of slowly varying. If it is a high frequency, then we cannot model it as a disturbance, then we call it as a noise. If it is a noise, then you have to check whether it is a Gaussian noise or a color noise, and then what would be the mean variance, covariance of that, right? So in that way, that is whatever the answer like unwanted signals, you should have some information about them. Otherwise, you cannot go by the controller design. You can ask the sir, what is the relation when you are designing a controller? Here we are designing a robust controller. What is the purpose? That is, even if these disturbing factors disturb the system, then still the stability and the performance will be preserved, right? Those are the, or that is the main objective of a robust controller. So if the robust controller has to bear or has to sustain all those unwanted or harsh effects, then it is your responsibility to bring in those parameters within the generalized plant. If you simply expect, that is, we are going to design a robust controller, but we won't include their effect within our plan, then how your controller will be made robust? The purpose of bringing all these like B1, B11 and all these matrices which are coming with this W term, that means we are including their effect within the generalized plant, and finally when you design the controller, you go to the M delta structure, then the robustness will be taken care of. That's why it is like we should always remain careful about the disturbance modeling or the noise modeling or for uncertainty as well. Okay, are you getting what I am saying? That is now in which regard I said, that is here. That is, if it is a time domain, I started the discussion, that is, if it is in time domain, then you have some more responsibilities compared to the frequency domain uncertainty, right? If it is already in the frequency domain, if you know that is this delta of S, it belongs to RH infinity, and then it has a norm, then that is your job is not that much, because finally we have to go for the M delta. Right from the beginning, you separate the delta and you find out the mapping PZW, okay? And then once you have the MS, we will design, soon we will learn the RH infinity controller design, and then finally you will have to only impose, that is the M of S, what we are designing. That is RH infinity controller means, first of all, the mainly two main objectives of any RH infinity controller. One is the MS, it must belong to RH infinity, right? And what is the second one? Not only this, along with that, if infinity norm must be less than the reciprocal of the infinity norm bound of the uncertainty, right? Where these are the two main objectives of any RH infinity controller.
So that will be equal or less than last one.
This one lesser than equals to. That is like it, I cannot say directly equals to, because it is uncertain, right? So if it is 5, then the controller which we are going to design, it will work for all the uncertainties without exceeding the 5, right? And here, see, that is, Sudarshan has asked an important question. You may also have a same doubt. Here, I wrote strictly less than, but here lesser than equals to. Do you know the reason?
The product should be less than.
Exactly. Here, why it is required? Because finally, I am going to use the Smolgen theorem. Smolgen theorem requires RH infinity norm of MS into delta S, that must be less than 1. Now here what I am doing, that is this delta of S, that I am saying that is lesser than equals to gamma. If finally it has to be less than 1, then this one has to be strictly less than 1 by gamma. Then only it will imply that is their product will less than 1. That is the reason. Sudarshan, is it now clear? So once again, like these are the objectives of any RH infinity controller. Again, here you can ask that is, sir, we thought RH infinity controller is a unique one. but you are saying any H infinity controller. Why you are saying any H infinity controller? So are there some categories of H infinity controller? So they are categories in the sense, why do you call a controller as H infinity? Because finally the closed loop systems fall or belongs to RH infinity, and it has a definite norm bound. That's why we call H infinity. Okay, and the controller which will maintain that ultimately norm bound of the closed loop system. That what kind of norm bound? H infinity norm bound. That is the reason why we call a controller or this kind of controller as H infinity controller. Should I repeat? That is why the name H infinity controller is given. It is such kind of a controller which, when is there in place, it will ensure that H infinity norm of the whole closed loop system would be less than a certain number. That's why the name has been given H infinity controller. Okay. In short, we call H infinity controller, but the reason is that when that controller will be in the loop, then the H infinity norm of the whole closed loop system is guaranteed to be less than some finite number. Now the main types of H infinity controller comes from how you are designing. Are you going to design it based on the state feedback? Like it is H infinity controller design depending upon the type of feedback you are using. If it is state feedback based, then it is called state feedback H infinity controller. Then the control law is nothing but that U equals to minus k of x. So you have to design such a k which will ensure that the closed loop system will become asymptotically stable, and then the H infinity norm will be less than a certain number. But the controller will come in this form only. But if it is now an output feedback, then U equals to k into y. Now, when you say output feedback H infinity controller, again the question will come, that is it a static output feedback or dynamic output feedback? Because static output feedback can also happen, right? So, if it is this category, static output feedback, then the representation will be U equals to k into y. So, here k is the output feedback matrix that you have to design. But most common or most famous is the dynamic output feedback H infinity controller, which we will learn. So there, how would you represent this U k of s into y? So this k of s we will design. Okay. So what you have learned? One is state feedback based H infinity controller. Another one is output feedback based H infinity controller. Now, depending upon whether it is static or dynamic, you can have static output feedback H infinity control or dynamic output feedback H infinity control. Okay. So so that's why I said any H infinity controller must have satisfied these two criteria. Okay. In the books or the papers, you will find that is most of the times they mention a very common term, loop shaping H infinity controller. Can anybody tell me that is what is the meaning of loop shaping? I know we haven't yet learned, but from your intuition, what can be a loop shaping H infinity controller? this is simply the block diagram. Suppose here H infinity, the K of S that we are designing by H infinity procedure. Okay. So now that is when you are talking about the performance. Performance means like I'm not at this moment I'm thinking about only transient performance. Okay. Transient performance or even in frequency domain can also be taken care of. Like in the frequency domain, that is if you will spread continuously. Okay. Now this is called loop shape. You can answer what is loop shape. That is, suppose this is the plot of the loop transfer function, designed loop transfer function. Okay. So you can answer what is the special. This is like a Bode plot only. We want, that is when the controller would be in place, then if you call L of S, that is the loop transfer function, is G of S into K of S. It must have a nice loop shape. What is the meaning of a nice loop shape? That means at the low frequency region, the gain would be sufficiently high but not too high. What does that mean? Suppose if you have an integrator in the system, then initially, that is, it will come like that. It will start from very high gain and this will come like that. It is not a good one. Why? Because what will happen if the gain is too high? Like, of course, for tracking performance, we need like some amount of gain. It shouldn't be too low. But at the same time, if it is too high, then it will amplify the noise. So that's why a nice loop shape means in the low frequency region, it will act as a low pass filter, okay, with moderate gain values. Then in the mid frequency region, this omega c, that means the cutoff frequency. Cutoff frequency means where the gain would be like the 63.2% of the final value, okay, or 1 by root 2 times of the final value. So then this during this crossover, this is called gain crossover, that is in the mid frequency range. The gain crossover, it will happen with the slope of minus 20 dB per decade. And then in the high frequency region, that roll off would be really sharp. Why? Because in the most of the noises will come in the high frequency range. So there, if you can't roll off the system gain, then they will amplify the high frequency noise. That would be then really a problem for us. So that's why we want that the gain at high frequency must increase. So okay, and because this is a dB scale. Okay, please be careful about that. In the negative dB means ultimately the absolute value is going too low. This is in dB. in a dB scale, if you have a negative gain, what does that mean? That is, it is in the fraction, right? In the dB scale, what you have, that is, if I write G dB, that is what is the expression? 20 log base 10 magnitude of G0 omega, right? Now, a negative dB gain means this will be a fraction. That's what we want. It is whenever in the book, why I am drawing like this, because if you find any books on papers on infinity loop shaping control, everywhere they start discussion with showing this kind of graph. That is, we want, like the loop ultimately will have this kind of smooth Bode plot or smooth frequency domain response like this. What is the specialty? As I just said, during the low frequency, it should behave like a low pass filter with a moderate value of gain. Why moderate value of gain is required? Otherwise, the tracking would be really slow. Okay? In the mid frequency, this cutoff frequency omega c, that is also a specification where you need the cutoff. Okay? And finally, this frequency, this is called the omega GCF, gain crossover. So, in the mid frequency range, that is, the gain will go down but not too high. Here we need a slope of minus 20 dB per decade, and in the high frequency we want a sharp or steep roll off. Okay, so that is called a theoretically nice loop shape. We will try to achieve a similar loop Bode plot response of the design control system. Okay. Now the question is that when you design the infinity controller, the LMI based or even Riccati based, it won't come automatically. That is the problem. You can ask the research, it is not that clear. What I mean to say, right? In the next two classes, we will learn how to design a infinity controller. I said many times that these are the two main objectives. Whatever infinity controller you design, first objective is that m of s must belong to H infinity, and second of s, it must satisfy H infinity norm bound. But these two doesn't imply that your loop shape would be a nice one. That is the main problem. So designing an H infinity controller will of course satisfy the first two objectives, but not of course this type of performance constraint. If you have to achieve any extra performance, you have to append some extra condition during the design. If you remember, last week I said multi-objective H infinity controller design. Why did I mention multi-objective? That too I explained. Suppose you wish to achieve an ISE performance, integral square error, then it would be a N2 norm minimization of the error signal. If it is a minimum energy control, or then you have to reduce the H2 norm of the U, right? If it is a disturbance attenuation, then you have to minimize the H infinity norm of the channel D2Y. That means the disturbance attenuation means, suppose the transfer function mapping from D0 to Y is noted by TD0Y, the transfer function from D0 to Y. Disturbance attenuation means the effect of D0 on Y must be minimum. What does that mean? That gain of that channel must be minimized. So disturbance attenuation in H infinity framework we represent by this. That is, suppose like this H infinity norm, you minimize the H infinity norm of the disturbance channel. Okay. In that way, whatever performance you wish to achieve, that has to be theoretically taken care of. Only H infinity controller design won't achieve or won't bring any extra performance. So this is a frequency domain performance which we are now talking about, a nice loop shape. If it has to be designed, or if this is desired, how will you do that? Any idea? The concept, okay, we'll write first. Or after looking into this, are you getting any idea about what is the loop shape? Or why I'm bringing two extra transfer functions?
We are adjusting the weight matrix such that we get this loop.
Right, but what is the purpose? Or what is the logic?
We are preferring some states and we are dispreferring some
No,
other.
here it is a frequency domain, so state is not coming into the picture. The idea behind it, that comes from your UG control only. Try to remember. All of you, that is, I have already given you the hint. That is, this core idea behind loop shaping that comes from UG control concept only. Okay, any guess? How do you design lead lag compensator? Tell me. No. During the lead lag compensator को पोल प्लेसमेंट क्यों होगा? वो तो completely frequency domain approach ना?
Determine the magnitude factor and angle factor into the transfer function by adding the gain margin.
Mostly gain margin, phase margin, and the cutoff frequencies. Like probably you might have forgotten. Let me show you an example. Suppose this is the Bode plot of a transfer function, GS. Okay, not at all a good one because as you can see that initially it gives a very high frequency, sorry, very high gain. Okay, now if I want it like that, what do you do? Earlier, here root transfer function means L of S means G of S into C of S. Just all of you try to remember the lead lag compensator design. Then how the question is formed, that is there is a transfer function, okay, maybe it is an unstable one or maybe marginally stable. You have to design a compensator so that certain gain margin is satisfied, certain phase margin is satisfied, maybe at the same time some cutoff frequency, resonance bandwidth, those things, right? And what is the procedure? That is, there is a, first of all, depending upon the gain margin and phase margin, you have to decide the frequency where maximum phase lead would be given, or phase lag, whatever, right? That sine alpha or tan alpha criteria. Based on that, that is, we come up with a compensator. Then here when you when you write C of S, that generally we represent S plus JC by S plus PC if it is only one stage compensator, only one pole and one zero. Then, so that the location of the PC and JC, how do you find that? Take from the angle criteria. Angle criteria means that is how much GN and PN is required. Depending upon that, first you will have to find that critical frequency, where maximum phase lead or phase lag would be given, that 10 criteria. Okay, from that we decide the controller pole and the zeros, or the compensator pole and the zeros, right? Then you check the Bode plot of the loop transfer function, right? All of you agree with that? That is when you decide this JC and PC. After that you form the loop transfer function LS, which is GS into CS, and you check. Then most of the times it happens that is after the first iteration, you, of course your response or the loop shape would be better, but not the perfect one or not the desired one. Then what do? First of all, you try to then adjust this JC and PC further. But with that also, if it is not met, then what do? You get one more pair, right? So if I write that is S plus JC1, S plus PC1, this into S plus JC2 divided by S plus PC2, two-stage compensator, right? In that way, so for a complicated plant, you may need n stages of controller also, right? And gradually you will see the loop shape, that means the Bode plot of the loop transfer function will gradually come towards the desired ones. Are you getting? Exactly the same thing is done over here. When you design the H infinity controller subjected to GS only, then your loop shape is never guaranteed. But now for getting or for achieving a nice shape of the loop, transfer function, you are intentionally bringing two weights. In the compensator, it was only one, as if that is here because it helps better. One is being pre-multiplied, one that is the G of S is being pre-multiplied with W1, post-multiplied by W2. These are one is pre-weight or pre-filter, another one is a post-filter. Okay, W1 and W2. Now, the type of the loop or loop shape which you need, depending upon that, we have to set or we have to design this W2 and W1. Now, if this is represented by G tilde of S, we will now design the H infinity controller not for GS but for G tilde S. This is called loop shaping H infinity controller. If you read from the books, like for any beginner, it is a little bit difficult to understand what is a loop shaping H infinity controller. So that's why I represented I explained in a very layman's term. When I read for the first time, for even for all the beginners, we have a common doubt, that is ये weight क्यों आ रहा है, हम लोग को weight क्यों लेना पड़ेगा. तो वही मैं बहुत दिन बाद जब तब मेरे को ये स्ट्राइक किया, अरे ये कॉन्सेप्ट कॉम्पेंसेटर डिजाइन की तरह ही है. So, loop shaping H infinity controller design means we are no longer designing subject for GS, but we are now going to design for G tilde S. Okay? So, what will happen? That is now for this also we will represent the, or we will draw the generalized plant diagram. So now it will no longer be only PS, it will become P tilde of S. These two are design factors. That means we have to, before you start H infinity controller design, you have to decide the weights W1 and W2. When they are pre and post multiplied with G of S, then as a whole it will be G tilde of S. If it is a state-based representation, then all your A, B1, C, all those matrices now become inflated with these extra terms, right? Are you getting what I am saying? That is, originally you had x dot equals to ax plus b1w plus b2u. Now A means that it was the A matrix of the nominal plan. And now you have two more transfer functions, so that A will become A tilde, right? And A tilde means that is, now it would be not diagonal, but now it would be a combination of A and A1, A2. A1 means suppose the A matrix of W1 and A2 means suppose the A matrix of W2. Now they are all in cascade, right? So A tilde, it would be the cascaded version of the W2 GW1. So accordingly you will have to write A, B1, B2, that way all of them will now be tilde version, okay? As if A tilde, B1 tilde, B2 tilde. Just try to think about the question. You might be thinking that अरे ये अगर MATLAB में हम लोग को करना पड़ेगा बहुत टफ हो जाएगा. Not at all, because all the commands are available. Only thing that is you have to know the procedure, that is what you are doing. Like when we will learn the LMI based edge infinity controller, we will learn for A, B1, B2, C1, C2, D1, 1. Now up to that, it is we are comfortable. You can think that is array, two more transfer functions are coming. Now how we will do? Then simply that is you have to find out the new ABCD matrices of G tilde, and after that the same LMIs will work. Only the variables will be replaced. Instead of A, B1, B2, C1, C2, now it will be A tilde, B1 tilde, B2 tilde, so on. As a whole, that is, this topic is called, since it is a design dependent upon the 4-block, this is technically we call 4-block edge infinity controller design, and if loop shaping is added, that means we are planning to include this W1 and W2. As a whole, this is a very famous topic, that is, which is called like loop shaping edge infinity controller design using 4-block structure. Loop shaping edge infinity controller design using 4-block structure. Any doubt so far? Check your notes and ask me if you have any doubt. Oh, that is just a notation as if here it must be L. This G and that G not the same, because here I use G of delta. So this is about the loop shape of the loop transfer function, right? The frequency domain response of the loop transfer function.
So that means that G tilde of S in a real robust system should be M tilde S, right?
M tilde? No, the loop transfer function. M means that it is already closed loop, right?
Yeah. Okay.
Now the case is that for simplicity I am assuming that is only Gs into Ks, or suppose as if into like G0s into K of S. Now it can be done on M of S as well. As you were thinking upon, that is whether it would be on L of S or on M of S, then that would be a little bit tougher. Okay. Here for simplicity, that is like to keep a track or to compare with the compensator design, that is I am explaining with the help of the loop transfer function. Okay. might be a little limitation. The same limitation for Dirichlet compensator as well. Can anybody tell me that is what is one of the disadvantage? I should not say disadvantage. The limitation of the Dirichlet controller, Dirichlet compensator. Related to loop shaping.
There's some trial and error. You have to keep checking whether or not.
Right, this is not one shot. Okay, good point. What else? You are checking the loop shape based on the loop transfer function, not the closed loop. Are you getting? We design a compensator depending upon AS, that means GS into CS. Finally, what do you expect? That is, when you close the loop, you have the input-output transfer function, that means R2Y GC by 1 plus GC. So ultimately you would expect that the closed loop transfer function GC by 1 plus GC will have a nice loop, but that is really tough. So when we design the compensator, or even here also, we exercise everything on the loop transfer function, not on the full input-output representation. So that's why what will happen, that is, the loop ultimately will attain a perfect shape, but after closing it is no longer only LS, it would be LS into I plus LS whole inverse. So in the closed loop it will deviate to some extent. That is the limitation. Are you ready? That means we are working on the loop transfer function, not on the closed loop transfer function. So what will be achieved for L of S, that means the loop shape which we will see for L of S, cannot match, or of course it will deviate something when it is LS by 1 plus LS, considering C so y. If it is mu, then LS into y plus LS whole inverse. That is the limitation. We are not working on the closed loop transfer function. We are working on the loop transfer function. That is the limitation. You can say that is, sir, if there is a limitation, we could have easily, we could have easily developed it for the whole loop transfer function. Then it would be really complicated, because then it would be both the numerator and the denominator controller will be involved, right? In the CISO case, if I say that is closed loop transfer function is GC by 1 plus GC. Now C is about C is to be designed both in numerator and in denominator. C is appearing, and denominator means it is going to be in the inverse term. So then the problem may not be a tractable problem. That is why that is most of the cases we apply or we follow this kind of design guidelines on the loop transfer function, so that L doesn't appear twice. Are you getting? That is this closed loop T. So here that would be L into I plus L whole inverse. If you have to guarantee the loop shape on T, then you have to work on this whole, which is really very difficult, because it will become a non-linear factor then. First of all, the product here also L, here also L, and that too it is the inverse of I plus L. So working directly on T is not an easy task.
That P means that is actually right.
Suppose if there is delta is not there, simply if it is a tracking problem, this is TRY. TRY, yes.
And that means we just have to prove that it is less than 1 by gamma. Finite H infinity norm of that should be less.
No, this is not in terms of H infinity norm, because I am now talking about the only loop shape. Satisfying the H infinity norm, that is a separate part, which is a completely different objective. Here, what I am discussing, that is, suppose H infinity design, all those things have been done, right? Using the procedures or the techniques, whatever already established. In addition, that is, in addition to achieving that H infinity norm constraint, if we want a nice frequency domain response of the closed loop system, then what would you do? We cannot directly work upon the closed loop system. We work on the loop, and which will ultimately be close to the closed loop. That is our motivation. That is, this loop shape, as you can see, that we are working on the loop, not on the closed loop. Okay. Of course, it will deviate to some extent, but not much. As a whole, this loop shaping is really interesting topic. And you say that is ultimately when you will work upon a real plan, I mean on a case study, then like how to design W1 and W2. That mostly depends upon our experience. So of course some guidelines are there, but how good say a W1, W2 you can design, that completely depends upon our experience. Okay. Now, okay, like these things are over. Like, we started the discussion from bounded real, and through that I have also discussed the preliminaries of edge infinity controller. Coming back to here, see this edge infinity, sorry, the in-delta structure. From that, we ultimately know that this edge infinity controller framework, it ultimately applies the small gain theorem, right? So, which need or which guarantees this one. But here again, what is the limitation? This uncertainty, it has to belong to RH infinity. Sure. If it happens that your uncertainty has a pole on the origin or on the j omega axis, suppose the uncertainty I am not considering the unstable uncertainty, but if it is marginally stable, then what will you do? Then like delta of S, it no longer belongs to RH infinity, right? And since it is uncertainty, you cannot directly do any manipulation to delta of S. So eventually, small gain theorem doesn't apply. So for such kind of uncertainties, you need some other type of technique so that like robust stability can be achieved, right? So that we will learn later. Then first of all, the concept of phase restricted uncertainties, that comes into the picture because of this only. Now suppose, like in the last semester, we learned positive real and negative imaginary, right? If you remember, the positive real or negative imaginary, both like allows poles on the origin or even on the j omega axis, right? Don't worry, those that who were not there in the last semester, that is little bit we will learn positive real and negative imaginary. At this moment, what I am saying, that is suppose you have a delta of S. If it is 1 by S, okay, maybe 1 by S square, okay, maybe 1 by S square plus 1, this kind of things. Then for this kind of delta, you cannot apply small gain theorem, right? Then how do you ensure robust stability? For that, you need some different type of techniques, like some other type of robust stability results, right? Because small gain theorem no longer applies. So now, if you see like this kind of uncertainties, they just a second, some space.
But if you know the structure of how uncertainty is, then how it becomes uncertainty. We know actually how delta is.
No, these are all unstructured, right?
Yeah, but now we write as delta as 1 by S or 1 by S square. So how can we say that it is uncertain?
No, this is again modeled. That is from the frequency domain response. If like from the pattern you are getting, that is okay. The delta can be modeled as 1 by S or 1 by S square.
Approximately it is like.
So here that is like as I wrote directly, you might have thought that is okay, delta is meaning exactly this transfer function, but this is delta is what we are writing, this is unstructured, that means the effect or the uncertainty, that is not identical to 1 by S. Here this is the model which we have designed, okay, that is the difference. And you see, I wrote on the WhatsApp portal this uncertainty modeling, the basic concept. Please check example 7.1, 2 and 3 from Skogestad group. I already wrote on the WhatsApp group, but maybe you haven't yet seen. Please check that one, okay? That is how we go for how to do uncertainty modeling. So the chapter 7 from Skogestad book, that is a good one, okay? And you don't have to read all. So whatever I have discussed most of the part, but with only one thing I haven't discussed, that is if suppose you have a system, then by using the frequency domain analyzer, you have got a frequency domain response of uncertain plant. From that, how do you find delta? For that, 2-3 examples should be checked. Only that part I didn't cover, okay? That is there, that's why I said 7.1, 2, 3, okay? Please look into those examples from Skogestad. That is easy, but just you have to look into that. There are mainly two types of phase restricted uncertainty. One is called PR, is positive real. Another one is NI, negative imaginary. This is quite evident. Positive real means suppose you have a seesaw transfer function G of S. Actually board clean के लिए एक को इधर फिक्स रहना चाहिए. अच्छा, इस कोर्स का टीए था किशन, राइट? Where is he? किशन को ही एक्चुअली ये काम करना चाहिए था. ये भी हो रहा है ना? अच्छा, ठीक, गुड गुड, आई लाइक इट. एक्चुअली मोइनक वाज अबाउट टू इंटरप्ट, बट वो बोल नहीं रहा है क्योंकि सोच रहा है कि वो बोलने से सर कुछ बोलेंगे इसलिए. अच्छा, प्लीज स्विच ऑफ द कैमरा. So now what we are going to learn is this phase restricted uncertainty. Okay, now phase restricted, for that this one thing is implied here, one thing is implied. What here? Delta, the uncertainty that is already represented in the frequency domain. Okay, may not be in the frequency domain, but it is now, it is about delta of j omega. Okay, delta of j omega, and it can be represented as a, either if it is a, it can be in the scalar, okay, it can be a matrix as well. Now that is if it is a dynamic, that is again it can be static or dynamic, right? So say for example, that is if you simply have a complex number j equals to x plus jy, from that you can find out the magnitude and the phase Okay, no need to convert into the frequency domain, or this is not a dynamic one. So when there is, you can expect a transfer function if original system, whether it is uncertainty or the system whatever, if it is a dynamic one, right? In the time domain, if something is represented by a differential equation, then you can expect that in the frequency domain you have a Laplace transform, right? So if the uncertainty is dynamic, then, and if it is linear, then we can expect its transfer function. But it is not that always we will get a transfer function. Okay. So phase restricted uncertainty, that it can be, that is, you can think about in either static or dynamic. If it is static, then that is you represent in this fashion, z equals to x plus iy, or maybe in that way you may have a matrix that is a delta, suppose z11, z12, z21, z22, that is what I am talking about. Just a second. You see, there is so many mix and matches are coming, right? So that's why, like today I wrote all the classifications so that you have a good idea about the different type of uncertainty. See, everywhere when this I am describing, then it is getting related with some other category. So that's why every time that is I am required to write the expression and then relate with the others. So that is the thing that is I want that you should learn. So phase restricted, what I say, it can also be static. Again, it can be dynamic. Right? In static case, if it is seesaw, suppose j equals to x plus jy delta. Again, it can be, suppose if it is a matrix, then z11, 1, 2, 2, 1, 2, 2. Complex uncertainty, static. Then you can answer this, well, already we have the real and complex. Why you are bringing this under this classification? Because now it has a definite phase bound. Regarding the phase bound, I am going to discuss this PR and NI. After I discuss, then you can immediately relate. That is why under the phase restricted cases we are discussing them. Okay. So that is for static, and if it is dynamic, then it is delta S. So here in that way you can write, suppose maybe delta 1 1 of this, delta 1 2 of this, delta 2 1 of this, delta 2 2 of this. Just as an illustration, I have written for 2 by 2 cases. Now, that is, you can ask, that is, what is the difference between this delta and this delta, right? So this delta, you see here, I can represent delta of j omega. For each omega, you will get a complex matrix, right? Static means you have only one unique complex matrix. There is no other changing parameter. But dynamic means corresponding to each and every omega, you are going to get a complex matrix, and then it will give you some magnitude or the gain and then phase angle, right? If it is seesaw, or if it is MIMO, then what would you do? Simply you have to go for the singular value decomposition. Again, that is a sigma. That means if it is a 2 by 2 case, so what would you do? That is this. representing them sigma of delta. That means singular value of delta. Now it will be a function of omega, right? So then one would be sigma max of delta, another one would be sigma mean of delta. This upper bar means max, lower bar means mean. Now it will also be omega function. If it is scalar, then of course you have, there is a magnitude plot and mode plot, right? But if it is a matrix, then we have to go for the singular value decomposition, and then you have to plot this sigma max and sigma mean, that one. So are you getting what is the difference between static uncertainty and the dynamic uncertainty? The static means you will have only one matrix that doesn't depend upon time, so no question of dependency on frequency. But dynamic means, of course, like if there is a dynamics, memory driven factor, so in the it has some relation with another variable. So if in the frequency domain, that means now it is sigma, delta of j omega. So if you plot the singular values, if you check the gains and the phase relation, they change from omega to omega, right? That is the case of dynamic. Anyways, now that is this phase. Whenever we write a complex number z, it has a phase associated with it. Now phase restricted, what does that mean? Similar to bounded real, that means this is a class of uncertainty for which we can define the norm, and that norm is bounded. From that only, that is, we get bounded real uncertainty. Okay, and then here phase restricted means phase will come everywhere if it is a complex number. But if you have a phase within a range, say for example minus 90 to plus 90, or suppose 0 to minus 80, in that way, if you have a class of transfer functions or uncertainties for which the phase angle remains within that zone for all frequencies, then they are called phase restricted uncertainties. Are you getting? That means it is a class of uncertainties for which the phase angle will be in a defined zone for all frequencies. Okay, so in that connection, there is what could be different type of phase restricted systems. We are going to learn this PR and NI. Let's say you have a seesaw transfer function g of s. Then from that we are writing g of j omega. Easily you can split it into the real and imaginary part. So I can write it RE of gj omega plus j into imaginary part of gj omega. Is positive real. PR means this real part of gj omega, it would be always positive for all frequencies, including both positive frequencies and negative frequencies. Okay. This translates into a phase angle criteria or phase angle bound. Phi of omega belongs to minus 90 degree to plus 90 degree for all omega belonging to R. Do you agree with this? That means if we have if the condition, first condition is there, by definition positive real means the real part of a transfer function is positive for all frequencies. That's how the name has been given. Once again, positive real. Real means the real part of a transfer function if remain positive for all frequencies, then that class of system is called positive real. Now I am claiming that if that is the condition, it will translate or it will imply a phase restriction of minus 90 to plus 90. You tell me, do you agree with this? Right. You check with this diagram, then you can immediately become convinced. Can you relate? How? real part is positive, right? So that means you have 4 quadrants, first, second, third, fourth. And positive real system means that is the real part will always be positive, at least non-negative. So the zone of existence here, you cannot have any component, that means you will find no component lying this side. So now, so this region, now in terms of angle, this is 0 degree, this is minus 90, this is minus 180, this is minus 270. So what is this region? Minus 90 to plus 90, because minus 270, that is equivalent to plus 90. So this region means a phase restriction of minus 90 to plus 90. That's what positive real system. Now this phase angle criteria that you can say only for schizopositive real systems. If it is MIMO, directly we cannot mention in terms of phase. Okay. Phase restricted term has come from this fact. This is one of the phase restricted class, which is PR. Similarly, there is one more NI we will going to learn. But first, you tell me whether this is clear to you. I wrote 3 small examples, 1 by S, 1 by S square, 1 by H square plus 1. Can you tell me which one or ones of them will belong to PR? 1 by S, think about the polar plot. If you have to decide whether a transfer function is PR or not, or even NI or not, you have to draw the polar plot. Okay? And you check, that is where does it lie. If it is 1 by S, then where would be the polar plot? On the negative imaginary axis, right? That will be the polar plot. So it is on the boundary line. J omega axis is the boundary line. At least it is not coming into this side. So that's why it is a positive real system, right? Now, if you plot 1 by S square, then where will be the polar plot? It will be here. Right? So that's why it is not positive real. Even if you think about the polar plot of 1 by S square plus 1, it will start from here. It will go to infinity. But while coming back, it will come back from the third quadrant, I mean from the negative real axis. So that's why it is not also positive real. Maybe half part belongs to fourth quadrant, but another half part will belong to the third quadrant. So that's why among these 3, only this is PR. These 2 are not. Are you getting? I can give you one more example. Here you have a purely complex 0, purely complex pole, and a pole on the origin. So, depending upon the pole 0 location, that is, it can be PR. But by checking this criteria, that is, let's suppose if you have to theoretically find whether a system is PR or not, what should you do? Simply you decompose the transfer function into real and imaginary part, and then you check whether the real part remains positive for all frequencies. Okay. So suppose this is a transfer function given to you. How to check? That is for what relation of omega z and omega p. I think most probably if omega z is less than omega p, for under that condition it would be PR. But that you must check it, okay? Not now, that is, it is a small home task. You have to resolve this transfer function into real and imaginary parts, and then you have to check whether the real part remains positive for all frequencies. Okay. similar to PR. Can anybody tell me what is a NI system? NI means negative imaginary. Then, like as we understood the meaning of PR, in the same way, can anybody explain the meaning of NI?
-0 to -1 experience.
That is, if the imaginary part remains negative, that is NI. Okay. So similarly, if I write NI, it means the imaginary part of the transfer function Gj omega, if it is lesser than equals to 0 for all omega greater than equals to 0. Now here you should mark a difference. That is, in case of positive real system, the definition covers the entire frequency, both positive frequency and negative frequency. But for NI systems, the definition is with respect to the positive frequency range only. That is the one main difference between PR and NI. Okay. Now, if that is the situation here again, that is, can I say that is this magnitude criteria will imply a phase restriction of -180 to 0 for all omega greater than equals to 0. If I write it, would you agree? Just you try to match with this. So this is 0 degree, this is -90, this is -180, this is -270. So what I am saying, that is, if the imaginary part remains non-positive for all positive frequencies, does it translate into a frequency phase restriction of -180 to 0? That is my question. Everyone, please verify with respect to the Nyquist diagram of NI. That is, here, this is the real and imaginary axis, right? So what is this zone? Where imaginary part, it is below the real axis. That means here, whatever imaginary number comes, there will be negative, right? So for any negative imaginary system, that is here what I am drawing, that is what is this for range. If you draw the polar plot, like suppose this one, or maybe this one, or maybe whatever, like this kind, arbitrarily I am drawing some polar plots, they will always, if they remains within this, then that is, you see their imaginary part, real part sometimes they are positive, sometimes they are negative, but imaginary part will always be non-positive, because if it goes above the axis, then only imaginary part can become positive. So that's what I say, for this class of systems, the imaginary part, the locus, I mean the polar plot, will always be below the real axis. Okay, that means the imaginary part is negative. Now, what is this zone? Doesn't it give you a phase restriction of 0 to -180? That's what the name has come. Is it clear to all of you? Think yourself. If you have any doubt, please ask. Finally, do you have any difficulty in understanding this one? If we take some examples, then it would be very clear. One more time, 1 by s. So it is traveling on the negative imaginary axis, right? If I take a for 1 by s, this is the polar plot. It must be NI. For 1 by s square, this is the polar plot. It must be NI. For 1 by omega square plus 1, right? This will also be NI. Now you see the difference. Earlier 1 by a square and 1 by a square plus 1, they were not PR, but they are NI, right? If I write one more transfer function, suppose 1 by a square plus s plus 1, then that is this one. that is also Ni, right? In that way, how can you theoretically check? Simply, whatever transfer function is given, you decompose it into real and imaginary part, and for Ni, you check whether the imaginary part remains negative for all positive frequencies. Okay, by definition only, not at all tough. By definition wise, you have to check. Now this identifying the PR or Ni property from the polar plot, it is a what this property, like this is a property and also a nice visual graphical representation, right? So if somebody asks you that what is the definition of a Ni system or PR system, you should not say that it is a system for which the phase angle contribution remains this. That is not the definition. What is the definition? This is the definition. And this definition translates into a property of phase restriction. Please mark the difference. Definition is one thing and the subsequent properties, they are some other thing. Like if somebody asks you that is what is the definition of a positive definiteness, you should not say that is a matrix with all positive eigenvalues is a positive definite matrix. No, that is the definition is something else, that is X transpose Ax is greater than 0 for all x, right? Here also the thing. The definition is what comes from the name, positive, real, negative, imaginary. That gives you this kind of phase restriction. So you can say this is a property. And this property actually it can be easily verified by means of the polar plot. So that's what I said, that it is a nice graphical interpretation through which you can easily detect the Ni or PR property of a SISO system. Is it fine? Now the question is that why we are learning these new things, right? That is why you need. What we are expecting, that is finally we know that is the robust stability means you have to check the robust stability of the M delta interconnection. Okay, earlier when both of them belongs to RH infinity, we had small gain theorem. Now we are thinking about those possibilities where this uncertain transfer function, I mean the delta, if it has poles on the j omega axis, then what will happen? Because then we cannot apply small gain theorem. So if fortunately the delta belongs to the class of phase restricted uncertainties, that means if it can be any type of it can be any type of other uncertainty where suppose if there are some complex number or matrices, it has different type of phases, but if the phase randomly varies, suppose if the phase varies within 0 to 2 pi, that means all 4 quadrants, then we don't have any particular result. But if the phase restriction is like that, either minus 90 to plus 90 or minus 180 to 0, then we have some good things available. Now, what is that good thing? That is in the M delta, this is the M delta configuration. Now, then the feedback, I mean this interconnection, at this moment is it a positive feedback interconnection, right? No negative sign is there, but it can be negative also. So it is either a positive feedback interconnection, mostly negative feedback interconnection, because we are familiarized with negative feedback interconnection only. But in some cases, it can be positive feedback as well. Now here what we are expecting, that is if delta S belongs to PR class or NI class, then we have a good robustability results. That is that for which we are learning these new things. Are you getting? When your delta S doesn't belong to RH infinity, but it belongs to a class of phase restricted uncertainties like PR or NI, we have robustability results. That is what we are going to learn. What is that result? Suppose if delta is a PR uncertainty, a phase restricted uncertainty of positive real time. If we can somehow design the controller KS, everyone please listen to carefully. Suppose the uncertainty is PR. If you can design the controller KS such that this MS is strictly positive real, then their negative feedback interconnection is robustly stable. Only one thing, that is I haven't yet said what you mean by strictly positive real, right? Or strictly negative imaginary. I'm going to define, don't worry. So here what did I say? Suppose delta S is positive real. Okay. Then if you can design a controller so that this MS becomes strictly positive real, then you are done. You don't have to even think about small gain theorem. By the PR-SPR stability result, its robustability will be guaranteed. This is a good thing, that is which is offered or which we can use provided your uncertainty is a phase restricted uncertainty. Or if you think about the situation, by the time let me explain what is a strictly positive real. We have learned what is positive real. Now if you have a subset within PR for which the real part is not only positive but strictly positive, then it is called strictly positive real. Are you getting? So suppose this is the set of PR systems within which you will have a further category. This is called asymptotically stable PR systems, right? Because all PR systems are not asymptotically stable. 1 by S, that is a PR, not asymptotically stable. Even this one, not asymptotically stable, but PR. So, if this is the whole PR class, then within which you will get a class which is A dot S dot PR, within which you have a further subset which is called SPR. That means strictly positive real systems are by defined asymptotically stable and they satisfy this particular condition. Example. Example. Simply, that is the easiest one is 1 by S plus 1, or in a generic form you can write K by S plus P, where both K and P greater than 0. Do you agree? So that is a strictly positive real system. So try to understand this Venn diagram. First you have the class of PR. It accommodates both asymptotically stable and marginally stable systems, right? Within which you have an inner circle which is asymptotically stable PR. Please don't think that asymptotically PR systems means SPR. No, there are some systems which are asymptotically stable PR, not SPR. So that's why you have a further subset which is the SPR. And then what is the stability version for which we are learning? The negative feedback interconnection of a PR and SPR systems is internally stable. That is the called PR-SPR stability theory, which we are planning to apply here. So look at this diagram. What I said, what is the stability result? A negative feedback interconnection of a PR and the SPR system is internally stable. For SPR system, I hope all of you will agree that now the phase restriction is even a little bit shorter, right? Open interval minus 90 to plus 90, right? Because if it is strictly less than 0, you come back here, sorry, strictly greater than 0, that means real part cannot be 0. Where the real part will become 0? If it touches the imaginary axis somewhere, then the real part would be 0. So strictly positive real means the real part cannot become 0. That means the polar plot cannot ever touch the imaginary axis at any finite frequency, right? So that means if the j omega axis is not touched, that means the possibility of getting plus 90 phase angle or minus 90 phase angle are excluded, right? So that's why for strictly positive real system, the restriction is even sharper, open interval minus 90 to plus 90. Whereas for PR, it is the closed bracket. That means, what is the meaning? Here is the closed interval, and that is an open interval. Okay, so that is the reason. Please try to understand the difference between PR and SPR. Do you now agree that for SPR the phase angle restriction will be open interval minus 90 to plus 90? That means the boundary cases are not excluded. Why? Because the polar plot cannot touch the j omega axis at any finite omega, because that is excluded or restricted by the definition, right? So that's why the boundary values minus 90 and plus 90, they are excluded. Similarly, if I wish to define strictly negative imaginary system, then this will be the definition. That is, strictly negative imaginary means the imaginary part, the value or the magnitude of the imaginary part must be not only negative, strictly negative for all strictly positive frequency. Here, everyone should be careful. See, why should we be careful? Because here you see that this definition is not valid at omega equals to 0. That is one of the main thing which is a tricky point. Once again, the definition of strictly negative imaginary system has been given, like this part is fine. whether which is from the name itself it comes, that is the imaginary part is strictly negative, but for which range of frequency? In case of positive real, we do not have any restriction on the frequency zone. It is for all omega belonging to R. But for negative imaginary, already we have seen that is for Ni, we had to define that is for only the positive frequency interval, because here it is we are testing, or here we are checking the values of the imaginary part. So that's why, that is, I hope right from this figure it is pretty clear to all of you. That is, if I don't restrict the phase angle, if I don't restrict the frequency of like 0 to only positive frequency, then what will happen? Even for this system, you will have the mirror image part like this, right? Simply that is for this transfer function 1 by a square plus s plus 1. What is the polar plot? Everyone please look at the board. This is the polar plot. Starting from this point, this omega equals to 0 and this point is infinity, right? And now mirror image means minus infinity to 0. So this is the mirror image part. Now here you see the imaginary part is all positive. That is the reason why for defining Ni systems, we have to take only the positive frequency branch, only the positive frequency interval. If you wish to take the both, then you cannot determine any sign. But that restriction is not there for positive real. That is the main difference between Ni and PR. Theoretical difference, that is, in the condition, we cannot include the whole frequency axis for defining Ni systems. Are you getting? The inverse mirror, inverse polar plot will have positive imaginary part. So that's why we have to restrict the frequency. Please write that point, then you try to analyze the SNI. SNI means the imaginary part should not be 0 at any non-zero positive frequency, right? So that's why if you now see my lines, they are slightly away from the real axis, right? That means the imaginary part should not be 0. So this is the zone where the polar plot of all SNI systems should remain. Are you getting? The difference with respect to this one, here the lines are touching the real axis. That means where imaginary part is 0. So for an Ni system, imaginary part can be 0 at a finite frequency. But for SNI, it should not be 0, right? If it is so, then when it is translated into the frequency domain criteria, the borderline cases, that means if it touches the negative real axis, so the borderline case of minus 180 phase, that will be attained. Similarly, if it touches the positive real axis, the borderline case of 0 degree phase, that will also be attained. But that we have to exclude because the definition says like that. Are you getting what I am saying? So that's why the SNI definition, that imaginary part strictly less than 0, that translates into the frequency domain criteria of open interval minus 180 to 0. That means the phase can be anything in between minus 180 to 0, but they cannot achieve or they cannot touch exactly 0 degree or minus 180 degree. Is it clear to all of you? Now coming to the main tricky point. When you are defining this property, I wrote that it is for the interval 0 to infinity open. That means while defining this strictly negative imaginary property, we are purposefully excluding those two frequencies 0 and omega. Can anybody tell me why? That is really a tricky question and one of the main important theoretical facts of NI theory. What did I ask? That is, when we are defining SNI system, we are specifically we are excluding omega equals to 0 and omega equals to infinity. Why?
Singularity.
Explain in a nice way so that we all can understand. No.
1 by s square equal to
You are simply getting confused with the example 1 by s. That is not.
1 by s square in place of 1 by s square. It will be 1
That
by
is only
minus
one
omega.
particular example where at 0 it doesn't exist. But it is whether it is 1 by s or 1 by s square. For 1 by s, what is the value of the imaginary part? That will always be negative, right? Real part is 0. So, but you said something that is not the answer of this question. What you said, that is something else.
So if we consider maybe a event can happen that it can lie on the real axis, but we are trying to avoid the actual real axis, so that we are excluding the 0. And for infinity, we don't know what.
Okay, one by one we will discuss. So here we are discussing for the real rational proper transfer function. You think about that what will happen for any real rational proper transfer function at omega equals to 0. That you take. From that, the answer will come. Exactly. For any real rational proper transfer function at omega equals to 0, you will find a real number. That means imaginary part is 0. Here we are defining SNI. We want the imaginary part to be strictly negative. Now, if somebody wants to include omega equals to 0, that is by default it is 0 for any real rational proper transfer function. Then can you define then SNI property? That is the reason. So Nitisha, you every time that is you make a mistake of this, you must be clear about what you answered and what is the answer of this question. Come. If I don't write, you cannot. It will be little difficult. How can you write what is the general structure of a real rational proper transfer function? Seesaw. G of s, how do you write? we are considering real, rational and proper. Inside proper you have two cases, one is by proper, another one is strictly proper, right? By proper means when this in and in they are same, right? That is the by proper. Strictly proper means this is in strictly less than n. And your relative degree means n minus n. RT means relative degree, that is n minus n. Now, if I have to find g of 0, g of 0 means g at s equals to 0, then ultimately what will happen? b0 by a0. It's a real number, right? Either positive or negative, or in some cases it can be 0. So if it is a real number, then what is the imaginary part? By default 0. Now in the definition of SNI, we want the imaginary part should be strictly less than 0. So that is the reason why you have to exclude the 0 frequency.
So here real part of S is also 0.
Real part of
S.
So here when I am writing S equals to 0, that means both sigma and omega. Good question. Here S means sigma plus j omega, right? So when I am putting S equals to 0, that means sigma 0 as well as omega equals to 0, both. If you have any doubt, then in terms of S, you simply convert it to G of j omega. Then it would be even easier. Instead of S, if you directly substitute j omega, and then finally if you write that is G of j omega at omega equals to 0, then also you will be getting the same thing, b0 by a0. So why we are excluding 0 frequency is now clear to all of you. Last question, why infinity as well? By looking at this transfer function, can you tell me that is a similar analysis is required to answer the question that why the infinite frequency also is required to be excluded? Can anybody answer? It will be Bm by 1. Very good. How do you get it? If we have to put, that is, you are thinking about g of infinity, right? So for finding out the value, here we are trying to find out g of s equals to infinity, right? Directly we cannot put that. So what should you do? You divide both numerator and denominator polynomial by the maximum degree of maximum power of s. So divide the numerator polynomial by s to the power n. Similarly, the denominator polynomial also by s to the power n. After dividing that, then you put s infinity. then you see what happens. If it is strictly proper, then always you will get 0. And if it is bi-proper, then you will get a real, that is what you said, that is Bm. When you will get Bm? If m equals to n. Otherwise, if m is less than n, then what happens? That is s to the power m by s to the power n, it will still have 1 by s to the power something, and then putting s infinity, it will go to 0. So this is the analysis. Everyone please try to understand what we have done. That is ultimately you have to find out g of infinity. That means g evaluated at s equals to infinity. How can you put s equals to infinity directly? Here you cannot substitute s equals to infinity, right? So that's why you have to divide both the numerator and denominator polynomials by the maximum power of s. After that you can put the limit, and then you will get a real number. If it is strictly proper, then always you will find that gain to be 0. If it is bi-proper, only then you will find Bm, right? Again, it's a real number. That means imaginary part is 0. SNI definition requires the imaginary part to be strictly negative. So that is why the omega equals to infinity should also be excluded in the definition. Nitisha, next time से ये और गलती नहीं होना चाहिए. Now the last bit I wish to hear from you only, why we are learning this NI or SNI. Finally, what is our goal? So similar to PR/SPR, here that is, if I suppose if your uncertainty belongs to the class of NI, then if we can design a KS so that your MS becomes SNI, then their positive feedback, please don't get confused. PR/SPR that works with negative feedback, and NI/SNI that works with only positive feedback. Okay. Once again, PR/SPR works with only negative feedback, and NI/SNI works with only positive feedback. Now here what we are expecting, if your delta S, if your uncertainty belongs to the NI class, then our objective is, or rather, we will try to design a KS so that your MS becomes a strictly negative magnet. Okay? And with this particular gain condition that we will learn later, it is called DC gain condition. If we can satisfy, then we can claim that the positive feedback interconnection of N and delta will be internally stable. Okay? That extra condition, that is actually N0 into N0 less than 1. Today I am not discussing. You simply write this is called DC gain condition, or simply DC loop gain condition. Why DC loop gain? Here what did I say? Oh, N, and instead of N I should have written delta. Sorry. Why loop? Because M and delta, they form the loop, and then N0 into delta 0, that means loop gain at DC frequency. That's why it is called DC loop gain condition. This extra gain condition has to be satisfied. This is a major difference, another major difference between the PR/SPR stability result and NI/SNI, because in case of PR/SPR, you don't have to satisfy any extra condition like this. Are you getting? In PR/SPR, we had the negative feedback interconnection of PR and SPR asymptotically stable. That is the end. But here, along with the NI and SNI criteria, this extra gain condition at omega equals to 0 is required, right? That is another major difference between PR theory and NI theory. For that same reason, This NISLI stability result is called a conditional stability result. So the takeaway point is NISLI stability result is a conditional stability result, whereas PRSPR is unconditional. NISLI stability result is a conditional stability result. Whereas PRSPR stability result is an unconditional one. Okay, guys, thank you for taking this extended class. Today I extended because so that I don't have to take a compensatory class for last Thursday. Okay. Next day I will recap the last